And welcome to lecture 21. So we are moving on to the new topic, and this is mostly about the tail bounds, what is known as tail bounds. Okay, so these are what is it? Let me start by saying what's a tail bound. So consider this probability distribution that is pictured here. You can think of this either as a PMF, in which case, if it's a discrete distribution, you can think of it as a PMF, and if it's a continuous distribution, you can think of it as a probability density function. Okay, both are different, and this is again a very common mistake that a lot of students make. If it's a probability mass function, then the value of this function at any point is equal to a probability. In fact, it is equal to the probability that your random variable takes that value. That's if it is a PMF, right? Then P of x denotes the probability that this random variable takes a value x. Whereas if it's a continuous random variable, and then this is a probability density function, then the value of the function at a point does not correspond to a probability. In fact, it can be much larger than 1 even. Then we have to, in a continuous random variables case, what we can only say is that if you take a small delta x interval around a point x, then the area of this strip will give you the probability that this random variable takes a value within the delta x neighborhood around that point. Okay, so that's the PMF versus PDF. Okay, now you try to think of the middle of a probability distribution as the point where the expectation of x is, Ex, which is sometimes denoted as mu if the random variable is clear from the context. Okay, so around that Ex, by the way, this is only one example of a probability distribution. There is no reason to think that the random variable should have very high probability around the expectation. In fact, the probability of a distribution of a random variable could as well be, something like this, right? Nothing prevents it from having, and your Ex will still be here. In fact, if you think about our usual Bernoulli random variable, it is either 0 or 1 with probability, let's say half each. Expectation, in which case the picture would look like 0 will have a half probability, 1 will also have a half probability, but your expectation is going to be in E of x, right? So there is no reason that there should be a lot of mass around the expectation. So this is only one example which may not always be true. Okay, yeah, but what is still, under all cases, what is, you still use the word tail to denote the area of under this curve, or the sum if it is a PMF, area if it's a PDF, for points which are far away from mu, something like a d distance away from mu on either side. The right side, it's called the upper tail, this shaded area. Area if it is a PDF, and just the series sum if it is a discrete random variable and it's a PMF. This is called the upper tail, and this is called the lower tail. And tail bounds are upper and lower bounds, most of the time upper bounds, but it could be both upper and lower bounds for this, right? So in this course, I think we will limit ourselves to mainly studying upper bounds for the tail distribution, which essentially also converts to a lower bound on concentration, in the sense that if the tails are upper bounded by something because it's a probability, then 1 minus that upper bound will turn out to be a lower bound for the probability that your random variable is within plus or minus d from its expectation. Okay, so an upper bound for the tail probability turns out also to be a concentration bound, a statement which says with at least this much chance the random variable is concentrated around the interval around the mean. Okay, yeah, so this I already said that the tail is usually defined relative to x, but it's usually, not always. Okay, and tail bound is is a bound for these probability guys. If it's a bound for x being greater than expectation plus some d, it's called an upper tail bound. If it is for if you are bounding probability that x is less than some Ex minus d, then it's called a lower tail bound. And most commonly we will go for combined tail bounds, which would bound the probability that the magnitude of x minus Ex is greater than d, which means it's either less than Ex minus d or greater than Ex plus d. Okay, so before we start our useful bounds, let's do a teaser bound. That's why I call it the bound 0. For any random variable x with a finite expectation, we can show that the probability that x is greater than or equal to, okay, so here this equal to is important, x is greater than or equal to ex is strictly greater than 0. Similarly, probability that x is less than or equal to ex is also strictly greater than 0. In fact, we use this in our expectation argument very much, right? Proof, you should probably pause and find out yourself what is the proof. Okay, I'm assuming you have found out the proof. You can easily prove this by contradiction. Okay, if this is probability of x greater than or ex is equal to 0, that means all the probability mass is concentrated before e of x, which means the ex couldn't have been that value. Similarly, here it's the same reason but in the opposite direction. Okay, now, yeah, by the way, if I replace this with a strict inequality, this is not true, because I can have a degenerate random variable where all the probability mass is concentrated in one value, in which case your ex will also be that one value, and probability that x strictly greater than ex can be in fact 0. Yeah, so this is just a, just a teaser bound, okay, but even for such a teaser bound to make sense, your e of x should be finite, e of x should exist. But this, remember that e of x is not always guaranteed to exist, right? We can even show this for a Bernoulli random variable. Think about something like a random variable which takes on values on the natural numbers, but non-zero probability is associated only with powers of 2. Okay, so if n is a power of 2 for some 2 to the power 1, so if for n equal to 2, 4, 8, 16, 32, etc., you have a probability of 1 by n. So 2 has a probability 1 by 2, 4 has a probability 1 by 4, 8 has a probability 1 by 8, etc. The PMF looks like what is there in this picture. Now, you can first, maybe you want to validate that this is indeed a PMF by checking everything is non-negative and sums up to 1, but half plus 1 by 4 plus 1 by 8, etc. sums up to 1, right? Easy observation. But you can also verify that the expectation diverges, okay? Your Ex would be probability that x equal to something times that x value, okay? So probability that x is equal to 2k times 2k, this probability is 1 over 2 to the power k times 2 to the power k. So you are summing 1 infinitely many times, so it's a divergent sum. So expectation does not exist, okay? In fact, yeah, you can easily construct random variables which are like this, right? This is only one template. Actually, I could have any random variable which kind of dominates this, which is more than 1 by n. You put this probability you put it 1 by n, but for something which is larger than this, then again this expression will go up. By the way, you don't even need this kind of thing. Even if you have something like a sum of 1 by n, it would still diverge and so on. So it's very easy to construct random variables for which Ex does not exist. Similarly, the fact that Ex exists does not guarantee that Ex squared and hence the variance will exist, okay? Even that may be true, but this I leave as an exercise. You try to design a random variable for which Ex is finite, but Ex squared is divergent, it is not finite. Okay, so yeah, with that introduction, we are ready to state one of the first tail bounds that most of us already know. Okay, this is called the Markov bound or the Markov inequality. In fact, the history of this Markov and Chebyshev bound, which is the bound 2 that we will study, is interesting. There is actually a debate as to who originally had this, invented Markov's inequality. Is it really Markov or was it Chebyshev? Okay, so Markov was, both are Russians, and Markov was a student of Chebyshev. Okay, Pafnity, Chebyshev, and Andrei Markov. But so some people think that, both of these inequalities were invented by Chebyshev and call this as the Chebyshev's first inequality. But we will follow the more common convention of calling it a Markov inequality. These are, again, because of this contention, this is difficult to pinpoint what is the time frame when these were discovered, but this is somewhere in this vicinity, right? Like surely 150 years ago, that these bounds are. Okay, so what does the Markov inequality tell us? It says that for a non-negative random variable x with finite expectation, okay, so if you ask me, never forget the hypothesis of this theorem. That is more important than actually, remembering this equality, right? I mean, this somehow, if you are regularly using probability, maybe, very common to you, but then make sure that these, before applying this inequality, you check both these hypotheses. Now, the finite expectation is not very difficult. People don't make a mistake there because the probability term also involves the expectation computation. So it somehow strikes you that, okay, this makes sense only if the expectation of the random variable is finite. But this non-negativeness can be forgotten. So, reiterate to yourself that Markov's inequality applies only to non-negative random variables, which means probability that x less than 0 has to be 0. Okay? It only applies to such random variables. Yeah, and for that random variables, there are various ways you can write down this, but I prefer to think of it this way. The interpretation when you write the formula in this format is that the probability that x exceeds some the expectation Ex by some alpha times. Think about alpha as 10 times. Probability that x is greater than or equal to 10 times its expectation is at most 1/10. Or probability that x exceeds 100 times its expectation is at most 100. Or in general, probability that x exceeds alpha times E of x is at most 1 by alpha. Okay. Now, this is kind of useful only if alpha is greater than 1. Otherwise, we are saying, giving an upper bound on a probability, if the upper bound is 1 or more, then it is a useless upper bound, right? Because probability is anyway at most 1. So this is useful only if alpha is very large. So at least, let us say greater than 1. And yeah, the proof of this Markov's inequality is very straightforward. You should remember it by just imagining that this is about splitting the Ex sum. At least in the discrete case, expectation of x is a sum. In the continuous case, expectation of x would be an integral. In both cases, the proof is about splitting the sum or the integral based on the value of x. Okay. So let's first check it for the discrete case. For the discrete case, your Ex is sum over x, which runs over the entire range of the random variable capital X, x times probability of x. Okay, so Px is nothing but probability that this random variable takes on a value x. This is equivalent to the PMF function that we started this lecture with. Okay, so this is the formula for expectation, the sum which gives you the expectation. When I say split, I only bother about this summation for the range when x is more than this guy. Okay, so I'm restricting this summation to, by the way, mu is just a shorthand for E of x. So I restrict this summation to x greater than or equal to alpha mu x times Px. Okay. Now, why can I put a less than or equal to, or rather a greater than or equal to here? Okay. So firstly, it looks like we are only, now this is a bigger sum and we are only taking parts of this sum, but still a lower bounding a subset sum or a lower bounding a full sum with a part of it is valid only if all the terms are non-negative, right? So here itself we are using the fact that x is non-negative, right? Otherwise, even at this place the bound is wrong, because if x had some lot of negative values, then this sum could actually be smaller than this sum. So here we are critically using the fact that x is greater than or equal to 0. And the rest is straightforward. Now, since your summation is in the range where x is at least alpha u, you can lower bound the x part inside the summation with alpha u and take it out of the summation. And this sum of probabilities, PMF values for x greater than alpha a, is exactly the probability expression that comes in the left hand side of the Markov inequality. Okay, so yeah, so it says E of x is equal to or is greater than or equal to E of x is greater than or equal to alpha u alpha mu times probability of x greater than alpha mu. So this is also, by the way, mu. So the mu, I think I should have maybe written one more step. So this says mu greater than or equal to alpha mu probability of x greater than or equal to alpha mu. Mu goes away, and if I bring this to this side, okay, this is the Markov's inequality that we want. Okay, yeah. So that's easy. For the integral also, it's the same thing. In general, your E of x is a, expectation again, because x is a positive valued random variable. It runs from 0 to infinity, x fx of x dx. Now I can lower bound it by the integral which only starts from alpha mu. Now from 0 to alpha mu, this is a positive quantity because x is anyway positive, because x is from the range 0 to alpha mu, and fx being a probability density. So the probability density is not upper bounded by 1, but it is still lower bounded by 0. So this is a positive quantity. So removing that can only reduce the value, and hence this bound is justified. Rest of the proof is exactly the same. Okay. Now, this kind of usual interpretations we have seen many times. If x satisfies the hypothesis of Markov's inequality, which means x is non-negative as well as it has finite expectation mu, then we can conclude that 10% with probability that x will exceed, x will be more than 10 times mu is at most 1 by 10, which means at most 10%. So that automatically means you give a lower bound. There is at least, I should say, there is at least 90% chance that x is before 10 mu. Similarly, if I take my alpha to be 100, then the probability that x will exceed 100 mu is 1 by 100, which is 1%, right? So you have 99%, at least 99% chance that x is within or before 100 mu, or 99.9% chance that it is before 1000 mu, and in general 1 minus 1 by alpha times 100, because I am using percentage chance, at least that much chance that x is within alpha mu. Okay. Now what are some of the limitations or disadvantages of Markov's inequality? X needs to be non-negative, and this only works for a subset of random variables. Expectation needs to exist, but that's okay. You are anyway, the bound is in terms of how much you will exceed the expectation. But this non-negative is kind of a serious restriction, right? And you can see that for a negative random variable which can be both negative and positive, it's very difficult to get such a bound, because you can easily make your expectation to be 0 by somehow, for any balanced random variable, and it is very difficult to bound the chance that you will be within some 10 mu as when your mu is 0. Okay, so it is in some sense an unavoidable limitation. A second limitation is that this 1 by alpha is a very weak bound. In many applications, we might need stronger bounds, but unconditionally you cannot get a stronger bound. In fact, you can easily create random variables where the Markov's bound is tight. Okay, maybe I'll also leave that as a exercise, right? Exercise: design a random variable, obviously a positive random variable x or a non-negative random variable x, such that Markov's inequality is tight. Okay, now the pros. What are the advantages? Expectation is one of the easiest statistics to compute. Okay, it's just the average, right? Average is something which everybody knows how to compute, and it is made even easier if you can decompose your x as a sum of simpler random variables whose expectations are easy to compute. Then E of x follows from by just adding them up because of linearity of expectation, without any assumption on independence of the component random variables, right? As long as if you can write your x as x1 plus x2 plus etc. some xn, your E of x will be E of x1 plus etc. E of xn for any sequence of random variables. You don't need any independence assumption or any other assumption. Okay, so that makes this bound, though only for non-negative random variables, and even though the bound is weak, applying Markov's inequality is the easiest of lot. Okay, a more important positive of Markov's inequality is that in some sense it's a mother of almost all the other bounds. Okay, almost all the other bounds that we will see, the proof will start with Markov's inequality. We'll see that already with the Chebyshev bound. We will see that when you see the proof of the Chebyshev bound. Okay. Now, for the Chebyshev bound, we also need to talk about the variance of a random variable. I'm sure, most of you know the definition already. Variance is defined only for a random variable for which, firstly, your expectation should be finite. Okay, because variance, definition of variance involves expectation. So that's a precondition. But it's also easy to see that if the first moment is unbounded, then the second moment will also be unbounded. Okay, so yeah, so finite expectation, E of x is the variance is defined to be the expectation of x minus mu the whole squared. Okay, yeah, you can also remember this as expectation of x minus mu the whole square. Mu is nothing but E of x. Okay, so mu is the mean, x minus mu is in some sense the deviation from the mean. If you take just expectation of x minus mu, you will get a 0 because the negatives and the positives will cancel out. So either you should take an absolute value, or being more analytic friendly, the most common measure of deviation is variance. Statisticians would actually use the square root of variance and call it as the standard deviation. Okay, so as the name suggests, that's the most standard among all deviation statistics. Okay, so that's variance. And then what does the Chebyshev bound tell you? It tells you that for any random variable x, now remember, this is now for any random variable, non-negativity is not needed. Okay, so that's one big advantage when you move from Markov to Chebyshev. But what comes additionally is that earlier we only needed finite expectation, but now we need finite expectation and finite variance. Okay, but again, you are very unlikely to make a mistake here because the expression involves both mu as well as sigma. So it would be kind of clear to you that you can apply this only if mu and sigma exists. Okay, yeah. And what is the bound? The bound tells you that the probability that your x will deviate from its mean mu by a factor, alpha factor of sigma, okay, where sigma is the standard deviation, the square root of the variance. So the probability that absolute value of x minus mu is greater than or equal to alpha times sigma is upper bounded by 1 by alpha squared. Again, remember, this kind of makes sense only for alpha greater than 1, otherwise this is a trivial inequality. So for example, it tells you that the probability that you will deviate, you will be 2 sigma away from the mean would be at most 1 by 4. Okay, so that's the idea. So this kind of agrees more with the picture that we have started this lecture with. Okay, this kind of a picture, the probability that, so this d, instead of calling it as an absolute number d, we, for Chebyshev at least, we call this as some alpha times sigma. Okay, and we say that the probability that your random variable is beyond this point, alpha sigma away from mu to the right or alpha sigma away from mu to the left, is upper bounded by 1 by alpha squared. Okay, so that's the Chebyshev bound. Proof is in fact even easier than Markov because it's a direct application of Markov's inequality. In fact, the proof of Chebyshev bound is just Chebyshev bound is nothing but the Markov inequality for the random variable y is equal to x minus mu the whole square. But in order to apply the Markov's inequality, we should check whether y satisfies the requirements for Markov inequality. Remember, x may not, because x is not guaranteed to be non-negative. But y is surely non-negative because of the square here. And the second condition for applying Markov's inequality is that expectation of y should exist. But that's equivalent to saying that the variance of x should exist or be finite. Okay, so now you can quickly verify that the Markov for y essentially tells you that probability of y greater than or equal to something times ey. That's something I am calling it as alpha squared. Okay, alpha squared ey would be less than or equal to 1 by alpha squared. This is not Chebyshev, this is Markov applied to y. Okay, now y I replace with what it is defined to be, x minus mu the whole square. Then ey turns out to be the variance, which is sigma squared. So this is alpha squared sigma squared. I'm just talking about the LHS here. Now this square I can replace with this, okay, magnitude of x minus mu greater than or equal to alpha sigma. This right hand side remains as 1 by alpha squared, and so you get back the Chebyshev inequality. Now, what is the positives of Chebyshev inequality? You have a slightly better decaying. It's like 1 by alpha squared compared to 1 by alpha for Markov. But compared to Markov, variance computation is not always as easy as a expectation computation, right? So even for a Bernoulli random variables, it's relatively easy. If you have x is equal to 1 with probability p and 0 with probability 1 minus p, expectation of this is very easily just p, 1 times p plus 0 times 1 minus p, which is equal to p. What would be the variance? The expectation of x minus mu the whole squared. Mu is p, right? So this is 1 minus p the whole squared times p plus 0 minus p the whole squared times 1 minus p, right? So yeah, there is a 1 minus p on both terms, and then there is a 1 minus p times p, and here there is a minus p the whole squared, which is a p squared, right? So this plus p squared. So this 1 minus p, this has a minus p squared that goes up, so a p remains. So finally this will boil down to p times 1 minus p. Here it is easy, but this is the simplest random variable you can imagine. But you see that comparing this EX calculation with this variance calculation is slightly more involved. But there is a very easy formula that you can actually check by just expanding. The variance turns out to be E of x squared minus mu squared. Okay, so that way if you calculate for this x, it would be E of x squared slightly more okay, yeah, but let me not do just a simple calculation. You can verify that. Okay, but okay, this is, when I say variance computation is difficult, this is not really the bottleneck. I mean, maybe with this bit more involved calculation, but the bottleneck comes from the fact that even if you can decompose your x as x1 plus x2 plus etc. some xn, what about the variance of x squared? Is it equal to variance of x1 squared plus variance of x2 squared plus etc. variance of xn squared? Is this true? Okay, the answer is again, it's not unconditionally true, but it is true if xi's are pairwise independent. Okay, pairwise independence is much weaker than mutual independence. So if you pick any xi and any xj, if they are independent, then you can actually conclude that the variance will also sum up, for variance will also respect the summation. Again, proving this is also important, but it's not very difficult. Okay, at least in the let me first tell in the case where the mu is 0. Otherwise also it's not very difficult. You subtract mu1 from x1, mu2 from x2, and mu n from xn. What you get here is x minus mu. So you work with that, nothing will be lost. Okay, but it is easier to describe in words when the mean is 0, so that your variance is nothing but expectation of x squared. Okay, so in that case, in order to compute the variance of x squared, you will have to compute, or the expectation of x squared, you will have to compute the expectation of this whole guy squared, right? This whole guy squared is what you will have to compute, which means now if you expand that term, you will get an x1 squared, x2 squared, all xn squareds. Those are fine. Those are the guys which will contribute these terms, sigma x1 squared or sigma squared x2 and so on. Those terms are fine. What is going to bother you are the cross terms, all the expectation of xi, xj, where I not equal to j. These are the terms that are going to hurt you. But if xi and xj, if any two of them in the list is independent, then E of xi, xj is equal to exi times exj, which is true. Not the expectation getting inside the product is true only if the random variables are independent. But you don't need mutual independence because you only need it to apply to two variables at a time. But once you split it into product of two expectations, each of them is 0. So they all cancel out and you get back this relation. So yeah, this variance sums up only if xi's are pairwise pairwise independent. Okay, so not in every context this will be true, and in those cases if they are not pairwise independent, you have to struggle with these cross terms, and it is because of that I kind of say variance computation is hard. Okay, this is not really the reason. Okay, now, but in fact, in the next lecture, we will spend most of our time trying to, if not do a variance computation, at least a variance estimation. In fact, modern mathematics always does that, right? Many a times we don't need to really have an exact value of the variance. It's good enough if you have an estimate, provided it's in the correct direction. Sometimes, most of the times, what we want is a upper bound on the variance, right? Because you can see, right? If you have an upper bound on the variance, then these results would still hold. Okay, so now, like the Markov intuitions, we can also tell concrete things about the Chebyshev inequality. We can say that if x is a random variable with mean mu and variance sigma squared, and variance sigma squared, there is 99% chance that x is between mu minus 10 sigma and mu plus 10 sigma. But remember, here there is a 10. This goes out to be a 1 by 10 squared, or a 1 by 100 chance of the random variable deviating outside of this. That's 1%, which means there is at least 99% chance that your random variable is within a plus or minus 10 sigma interval around the mean. Similarly, if you are ready to go to a plus or minus 100 sigma, you can get 2 more digits of accuracy, 99.99% accuracy. Okay, now we will not really focus on actually applying the Chebyshev bound in this class, but just before proceeding, I thought at least one easy application. So in fact, rather it would be one easy application on the max cut problem. Okay, so recall that in our very first or second or even the very first lecture, we studied this problem and proved that any graph G with m edges contains a cut of size m by 2. So cut you can think of as a bipartite subgraph of G, and the size counts the number of edges which cross this bipartition. How did we prove this? We proved this by random coloring, but surprisingly this is about edges, but the coloring was on the vertices. We colored each vertex of G independently, okay, and uniformly at random with color red and green. So at each vertex you tossed a coin. If it was head, a fair coin. If it was head, you colored it red. If it was tail, you colored it green, and this was independently repeated for every vertex in the graph. And what edges did you pick to be in the cut? The edges which connected a red vertex with a green vertex. Okay, such edges were included. This is easily seen to be a cut. The red vertices will form one part of the bipartition, and the green vertices will form the other. How did we estimate the size, or how did we argue that this will produce a cut of this size? In fact, we did not argue that this will produce a cut of m by 2 size. What we argued is that the expected size of this cut is m by 2, which is and once you prove that, I'll anyway detail that also, but once you show that the expected size of this cut is m by 2, we can conclude that there is at least one cut with size m by 2. Okay, in fact that's our teaser bound. Okay, this is our teaser bound. We know that there will be probability that there is an x whose value is at least the expectation is greater than 0, which means such an x will exist. Okay, so that was our argument there. And how did we show that the expectation is m by 2? We split x into a sum of m indicator random variables, x1, x2, xm. There was one random variable for each edge. So xi was 1 if the ith edge turned out to be between a red vertex and a green vertex, and 0 otherwise. Hence, expectation of xi is nothing but probability that xi is 1, which is half. Right, either red green or green red. So 2 out of the 4 equally likely cases, and hence the expectation of x because of the linearity turned out to be m by 2. So this is what, and this was enough for us. This implied that there exists an x such that there exists an x with more than m by 2 edges. That was enough. But now let us apply variance and Chebyshev bound to it. What is the variance of this random variable x sigma squared x? Now here, fortunately, these also turn out to be independent. We because okay, why do I say that this is independent? Okay, while making this note, I did not realize that there is a complication. If your ith edge, say your E1 is like this and your E2 is like this, then it is easy to see that the random variables x1 and x2 are independent, because whether E1 is red or included into your set 1 or 0 only depends on the color of this vertex. Let me call it x1 and this is y1, only depends on x1 and y1's colors, whereas E2, whether it will survive or not, whether it is one, whether x2 is 1 or 0, depends on some two other vertices x2 and y2, and because of their independence of the tosses, these are independent. So here it is easy. But what if your E1 and E2 were like this? Okay, so they had a common neighbor x. Okay, so in this case also you can verify that x1 and x2 are independent. First it is easier to argue based on a conditional argument, right? So suppose your x and y1 are already colored, which will automatically determine whether E1 is in your set or not. Now the survival of E2 now depends on the color of y2. If y2 is same as the color of x, then it dies, which is with probability half. And if the color of y2 is different from x, it will survive, which is also with probability half. So the fact that this probability is still half is enough to conclude that this is conditionally independent. Okay, so the probability that x2 is equal to 1 given x1 is equal to 1 is equal to probability that x2 is equal to 1 given x1 is equal to 0, which is equal to the unconditional probability that x2 is equal to 1, this is equal to half. Okay, so yeah, because of this reason, here again there is a independence. In fact, I only need to argue about pairwise independence. Right, so there is, in fact, is there a mutual independence here? That's a good question. Think about these three edges, say E1, E2 and E3. Now if you know that E1 and E2 are in the cut, okay, which means let's say this is red, okay, that means this is red, and and if this is red, then this is the opposite color, green. That automatically tells you that E3 is not. Okay, yeah. So this is in fact a nice example. You have pairwise independence, but no mutual, not even three-wise independence. Okay, not even three-wise independence. Okay, but pairwise independence is sufficient to apply this formula, that your variance is equal to sum of the variances. Variance of each of them is easy to calculate. We already said that it is p times 1 minus p, so it's half times 1 minus half, which is 1/4. You add up all of them, you get variance m by 4, and by Chebyshev inequality, what do we get? We get that the probability that x will deviate by from m by 2, which is mu, by more than alpha times the variance, not the variance, the standard deviation, which is the square root of this, hence it is root m by 2, is at most 1 by alpha squared. In particular, like if I take alpha to be 2, then I'll see that, okay, the probability that this random variable will go by a root m distance away from its mean is at most 1 by 4. Okay, now suppose that we had more than pairwise independence, right? We had mutual independence. We just saw that it is in fact not the case, but when I was preparing this note, actually I forgot about it. I somehow had a slip of mind and I assumed it is independence. That's why I was using the same number. But now in this digression, think of your x to be some x1 plus x2 plus etc. xm, sum of m random variables which are mutually independent. Okay, this will mutually independent, right? Much more than pairwise independent. And then instead of, let me do this computation. Okay, now calculate what is x1 minus ex1 the whole power 4. This is the difference. Okay, if it was square, then this is just a variance computation. So yeah, the name for this is the fourth central moment. If it was just e of x1 to the power 4, you would call it the fourth moment. Since you are subtracting out the mean and then taking the fourth power, this is called the fourth central moment. It's easy to compute, right? Because you already know ex1 is half. Remember, I'm only talking about one of these guys, okay, not the entire sum. Okay, so one of these guys will turn out to be half to the power 4 times half plus again half to the power 4 times half. So it turns out to be 1 by 16. Now, because actually you don't even need mutual independence. Suppose you had 4 wise independence, okay, which means every combination of 4 random variables was independent. Then again, while doing this computation, you will actually expand again, think for a moment that you have 0 mean random variables and you have something like x1 plus etc xm the whole power 4. Okay, so in these cases there would be terms like x1 power 4 plus x2 power 4 plus etc xm power 4. They are okay, they are the guys we want in the summation also. But then there are terms like x1 x1 x2 cube. These guys, if they are independent, then your e of x1 will be 0, hence they will vanish. And even because you have 4 wise independence, things like x1 x2 x3 x4, they are also okay. There is one problem case where you have x1 squared x2 squared kind of guys. Okay, so these are more difficult to deal with, because even if you go inside of this, you will have ex1 squared plus times ex2 squared. Those may not be 0, right? Yeah, so even 4 wise independence will not guarantee this m. So I should actually probably what I should do is I should not, I only want to make one point. I should not worry about all these things. I should say, suppose, take this as the assumption. Okay, suppose this also is not needed. Okay, so suppose your x minus m by 2, the fourth central moment, was bounded, was some m by 16, right? Then I can now, okay, now this is unnecessarily complicated. Why should I now use m by 16 and all? Suppose this fourth moment was something like, gamma power 4. Let me just call it that way. Then you apply Markov, and this I'll just call it as the mean, mu. Okay, so now you apply Markov for x minus mu to the power 4. Remember, in order to prove Chebyshev, we applied Markov inequality for x minus mu to the power 2. So here we only need the fact that this x minus mu to the power 4, its expectation should exist. I call it gamma to the power 4. Now, this tells you that, Markov is exactly this, which translates to probability that x minus mu to the power 4 greater than or equal to alpha. Okay, let me call this as alpha power 4, because I'll anyway take the fourth root later on. Why call it alpha? Let me just call it alpha power 4. And what is this expectation? Ey is nothing but gamma power 4. Okay, so this means I'll get magnitude of x minus mu greater than or equal to alpha gamma. Okay, so that's all. That's all. But let me write one special case. X minus mu greater than or equal to even 2 gamma will be 1 by 16, right? So I actually did this mainly to highlight this point, that the higher moments, if they exist, they give better tail bounds than the Chebyshev. Okay, so for Chebyshev you need only pairwise independence, so it's applicable in a larger context, especially and also not in every case where variance exists, it is guaranteed that the fourth moment should exist. But if the fourth moment exists and is also easy to compute, then by using that you may get a better bound than what the Chebyshev bound gives you. So I don't want you to think of Chebyshev as one single bound which works for the second moment. You can extend the same idea to any even moment. Okay, this even moment is required because of this guy. In fact, odd moments can turn out to be 0. Yeah. And what is the highest moment that we can think about? In fact, we can extend this for random variables which are really well behaved, and that is what will give the Chernoff bound. But I see that we are at the 45-minute mark, so let's postpone this Chernoff bound to the next lecture. Okay, maybe lecture 22. Okay, thank you.